Alright guys, this video is a review about the charge and oxidation state. It's a combination of, it's some materials from chapter 3 and chapter 4. Okay, so I know you guys get confused about, the charge and oxidation state, those tiny numbers in the formula, those kind of things. Let's take a closer look of those the concepts. The first thing is the charge. When we talk about the charge, it's for ions only. Oxidation state, it's for elements. Okay, so when an element loses electrons, it's gonna be positively charged. If elements get electrons, it's gonna be negatively charged. Let's take a look at this example. If you are talking about lithium, in most of the chemical reactions, it's gonna lose one electron to give you lithium cation and one electron. So we are talking about when we talk about the oxidation state for lithium, and that is positive one. Okay, that is a positive one. So that is how we take a look at the oxidation state for elements. And one more example: if you have oxygen, for oxygen you usually get 2 electrons to get O2 minus. Now, the oxidation state for oxygen, because it gets 2 electrons, it would be negative 2. Okay, so this is how we, refer the oxidation state. We write the small number, either positive or negative number, on the top of the element symbol, and that is how we tell whether that's the oxidation state. Now, what's the connection between the charge and oxidation state? Here are the 2 rules that you need to follow. The first one here is if you have only one element in ion, then the charge equals to the oxidation state. Take a look at these 2 examples. Lithium lose 1 electron to give you lithium 1 plus, okay? Lithium cation. Now, when you look at the charge is positive 1. Because this ion has only one element. The charge is the oxidation state. So the oxidation state for lithium is positive 1. Oxide, because it gets 2 electrons, the charge for oxide would be 2 minus. Okay, this is a charge. We use a small number on the right upper corner to tell the charge of this to show the charge of this ion. Because this one has only one element, so the charge equals to the oxidation state. So the oxidation state for oxygen is negative 2. This is rule number 1. Rule number 2. Polyatomic ions charge equals to the sum of oxidation state. This actually is related to the calculation we did for some of the for the oxidation states of involving polyatomic ions. Think about this. Perchlorate. We saw this example in our class. We said that the perchlorate is 1 negative charge. We will see this polyatomic ion in the following slide. Well, this is a charge. The negative sign here is the charge. It tells people that this is 1 negative charge for perchlorate. All right. Now, remember what we did. What we are trying to do is we try to find out the oxidation state for chlorine. And the oxidation state for oxygen is usually would be negative 2. Because the charge for polyatomic ions, the charge equals to the sum of oxidation state. So the question mark plus negative 2 times 4. That equals to the negative 1. Okay, why do we have to multiply by 4? Each oxygen has negative 2, right? Now you have 4 negative 2 charged atoms or ions in this formula, so you need to multiply by 4. Now if you do the calculation, you will realize that oxidation state for chlorine is positive 7. So actually when we did the calculation, we are using this rule number 2. All right. Now let's take a look at one more example. If you have NO3 minus, again you have one negative charge. If you don't know the oxidation state for nitrogen, then you can set up the question mark plus the negative 2 times 3 equals to negative 1. The charge equals to the sum of the oxidation state. So the question mark equals, if you do the calculation, question mark, the value for question mark is positive 5. So oxidation state for nitrogen is positive 5. This is the simplified periodic table. I ignored the actinides and the naphthenides. So let's focus on the main group elements. For group 1 elements, the most common oxidation state is positive 1. All right. We do have some exceptions in hydrogen. Okay, hydrogen sometimes you can't get one electron from metal element to get hydride. Okay, so in this case, oxidation state for hydrogen is negative 1. But for lithium, sodium, potassium, rubidium, and cesium, these are always positive 1 charged, which means they are the oxidation state for those 5 ions. Okay, let me write it here. Lithium plus, okay, sodium plus potassium plus rubidium plus rubidium and cesium plus. Okay, so for all of these 5 ions, oxidation state is always positive 1. For beryllium to barium, those 5 elements, in most of the chemical reactions, they always lose 2 electrons to get the 2 positively charged ion. So therefore, the oxidation state for those 5 elements is always positive 2. Aluminum, gallium, and indium, those are 3 elements. Usually they lose the 3 electrons to get the 3 positive charge. So the oxidation state for those elements is usually positive 3. Nitrogen, phosphorus get 3 electrons from other elements, so the most common oxidation state is negative 3. For oxygen, sulfur, and selenium, they always get 2 electrons, from other elements, so the most common oxidation state is negative 2. For halogens, fluorine, chlorine, bromine, and iodine, they get 1 electrons from other elements, so the most common oxidation state is negative 1. Okay, negative 1. Fluorine is always negative 1 oxidation state, but there are some exceptions about the chlorine, bromine, and iodine. Sometimes they can get positive oxidation state, like we see here. Okay, like we see here. So these are the common oxidation states of those main group elements. All right, now let's move on, and now we know the difference between the charge and the oxidation state now, and also we know the connection between them. Now let's do some practice. Let's try some binary formula of the binary ionic compound. Okay, and those 2 tables are from your textbook. Okay, those 2 tables are from your textbook. This table shows us those common charges of those elements from group 1, group 2, and group 3. And this table is the charges of those some nonmetal elements. Now let's do some practice and see how we find out the formula for those binary ionic compound. Meanwhile, by the way, the binary ionic compound means you have only 2 elements in this compound. Now let's see, lithium and chloride. Lithium chloride, you have 1 positive charge and 1 negative charge. So when you bind them, the whole This formula will give you the neutral compound. So it's balanced. It reflects the ratio of those two elements in this formula properly. Okay, so this is the right formula for lithium chloride. This is easy. Now let's take a look at this example. Lithium and oxide. One lithium cannot be used to balance the two negative charges of the oxide, so you need one more. Okay, you can always increase the number of those ions, either cations or anions, to find out the right number of those ions for the formula. Now you have two lithium cations, two positive charges. Now it's enough to balance the two negative charges of this oxide. So it will give you a formula lithium 2 oxide. We have this 2 here to tell people that in each one of the formulas of the lithium oxide, it has 2 lithium cations. Okay, so this 2 reflect the number of the ions in the binary ionic compound formula. Let's see more examples. How about magnesium 2 plus and nitride and 3 minus. Now this is a little bit complicated because as you can see that apparently 2 plus won't be able to balance the 3 minus, right? Now you can try to increase the number of the magnesium if you want. Magnesium. Now you have 2 magnesium 2 plus. Total charge is 4 positive charges. Still, it's kind of awkward for you to find the right number to balance the 3 negative charges. Now let's get one more. Now you have 3 magnesium 2 plus. Now 6 positive charges, 3 negative charges. Now what you need to do is just get one more nitride. Now 6 positive charges, 6 negative charges. It will give you the right formula. Magnesium 3 and 2. Alright, this is how we do the binary ionic compound. Alright, okay, let's see more examples about the binary ionic compound, especially those binary ionic compounds involving transition metals. We know transition metals could have more than one oxidation state. Okay, for instance, iron could be iron 2 plus, iron could be iron 3 plus. Then, how do we write the binary ionic compounds involving those transition metal ions? Again, this table is from your textbook. You follow the same rule. All right. For instance, you have iron 2 plus and bromide. Okay, Br 1 minus. Now what you need to do is just change the number of the bromide from 1 to 2. Now you have 2 negative charges. You have 2 positive charges, so it will give you iron 2 bromide. Okay, iron Br2. Okay, more example. If you have cobalt 3 plus and O2 minus. Okay, now apparently 3 positive charges cannot be used to balance the 2 negative charges. Let's increase the cobalt. Okay, get one more cobalt. Now you have 6 positive charges. How many 2 negative charged oxide should we have to balance them? You should have 2 more. 3 oxide, 2 cobalt, so the cobalt 2 O3. Alright, this is how we do it. You just need to focus on the charge. You just need to focus on the charge. Now, for those ionic compounds involving polyatomic ions, okay, couple of things that we need to pay attention. This is a table from your textbook. These are the formula and the charges of those polyatomic ions. When we talk about the polyatomic ions, why do we write the formula like this? Okay, it's because this, for instance, this chromate, the chromium and oxygen, because they are binding with each other. So that's why we write the formula like this. Even if they are, dissolving in water, they are gonna stay together. Okay, so this is polyatomic ions. You won't dissociate them. In the next video about how to write the complete and net ionic equation, we'll take a closer look. Okay, but here in this table, I do need you to remember the formula and the charge of those common polyatomic ions. Then, how do we write the formula for those ionic compounds involving those polyatomic ions? Let's use the example. See, if you have calcium 2+, and the nitrate, NO3-. How do we write the right formula between these two? You follow the same rules, okay? You just focus on the charge. Take a look at how many nitrate, how many calcium you need to make sure that the whole formula is neutral. Now you have 2 positive charges and 1 negative charge, so let's increase the number of nitrate from 1 to 2. Now you have 2 nitrate. Now you can put them together. Calcium nitrate 2. Now 2 negative charges, 2 positive charges. The whole formula gives you a neutral molecule. This is good. This is the right formula. All right. Again, this 2 tells you that in each one of the molecule you have 2 nitrate. And we always use the parentheses to isolate the nitrate in this formula because that's the whole species. Okay, that's the whole species. If you write the calcium NO3 2, that's gonna be a little bit confusing, right? Because you have a 3 here. How do you got 2 here? How do we understand them? So you need to use the parentheses. All right, let's see more examples. Now, how about ammonium and how about carbonate? Okay, 1 positive charge and 2 negative charges. Now, you increase the number of the ammonium to 2. NH4 plus. You have 2 now, 2 positive charges and 2 negative charges. It gives you ammonium 2. Again, we use the parenthesis to isolate that, to indicate that this is a atomic ion, and for carbonate, it's just itself. Okay, if you have more than one, if you have more than 1 polyatomic ions, you use the parenthesis to isolate them. Let's say more example. Let's see. How about barium 2+ and the phosphate. Okay, phosphate right here. Now, how do we write the formula? We increase the number of the barium 2+ like we did for binary ionic compound. Is this balanced? Apparently not, right? So you further increase that number of barium 2+ to 3. Now you have 3 barium 2+. How many phosphate you need to balance the charge? You need 2 phosphate 3-. Okay, you need 2. So now it gives you barium 3 phosphate. Again, because we have more than 1 phosphate, we use a parenthesis. Okay, so this is how we write ionic compounds involving polyatomic ions. Hopefully, this video can help you get better understanding the charge, oxidation state, the meaning of those numbers. But again, if you have any questions, please let me know. Thank you, guys.